So the introduction, basically the objective of this lab was to analyze the motion of a falling slinky by comparing the observed experimental data from Tracker with the model data from GlowScript. Our goal here is to prove that the slinky only falls when the top meets it, so when the top reaches itself. A summary of the results, all of this was proved, so the slinky does not fall until the top of the slinky meets it or reaches it. Okay, so here are some formulas. We have the net force formula, so dp over dt, and you can derive that and eventually get mass times acceleration. We have the velocity update formula, which is the final velocity equals initial velocity plus acceleration times change in t. Then we have the position update formula, so r final equals r initial plus the v average change in t. These will be used in GlowScript, but also we have like tension being discussed, and we will be using the force of gravity, mg, negative direction. So in Tracker, I was unfortunately unable to show the video because it was interfering with this recording, but as you can see, I calibrated it to be to the man standing to the left, and I tracked the point mass of the slinky up until it fell. So as you can see, there is constant motion until around 6.5 seconds when the top of the slinky meets the bottom portion and the slinky falls altogether. In GlowScript, here are some important formulas I added in. So the mass of the ball, I included that. I included the position vector, which was I retrieved from Tracker. I also included the gravity, which was 9.8. B down here is just something that I was guess and check. I just had to put something in once everything was all said and done. So up in blue, this was the first portion of the code where I wanted to show that up until the top of the slinky reaches it, that there is constant motion. Basically, the slinky is not moving. So I said while t is less than 7 seconds, and then I included all of these formulas, which as we've seen before, like I said, we're including the velocity and the position update. You can see those down there. And then in the yellow, I then did a second iteration of the code, which included when the slinky began to fall. So when the top met, like when the top of the slinky reached itself. So basically when the slinky was compressed. And once again, we're including the velocity update and the position update and just some important formulas to show that it is indeed falling. So here are the GlowScript results. As you can see, up until 7 seconds, the slinky is not doing anything until it falls because it is now compressed at this point. All right, so now we have some comparisons. I did put both of these graphs, so the one from Tracker and the one from GlowScript, into an Excel, and as you can see, they are very different. But the most important thing here to note is they're similar in the fact that you can see it around the same point, which is when the slinky is compressed. They are falling. You know, there's constant motion. The slinky is not moving at all up until roughly about 7 seconds in this in the Excel graph. So that's what's most important to take here, is that the slinky is not moving at the same time in both Tracker and GlowScript. So as you can see, despite them being different, there is something to take away from both of these graphs. So the errors, though, from this, I said I could have tracked it wrong. I also might not have accounted for every external force. Actually, I know I didn't account for every external force acting on the slinky in my code, like air resistance. But it does, like I said, they showcase that the slinky, both experimentally and computationally, does not start falling until the top reaches it. Okay, so what does this mean? What do all these results mean? Like I said previously, the slinky does not drop until the top meets it. The bigger question here is why. This happens because the tension of the slinky pulling upwards and the force of gravity are balanced until the slinky was compressed. So when the slinky is compressed, that's when it starts falling, aka when the top reaches it. So what if? What if a mass, such as a ball, was attached to the end of the slinky? What would happen to the ball? Interestingly enough, the ball acts much like the bottom of the slinky. So basically, until the top of the slinky reaches it, meaning the slinky is compressed, the ball remains motionless, but once the slinky compresses, the ball falls alongside the slinky, so they fall together. And this is because the weight force on the mass, in this case the ball, is balanced with the tension of the slinky. So that's why it doesn't move until that slinky is then compressed. So thank you so much for watching.